Imagine racing through the universe, faster and faster, yet always falling short of catching the one thing that remains perpetually out of reach: light. No matter how fast we go, there's always one thing we can never catch: light. It's the fastest speed anything can travel in the universe, unwavering in its constancy. Whether we use a flashlight, gaze at the moon or sun, or measure the light from a distant galaxy billions of light years away, the speed of light remains unchanging. When we look into the universe today, we see points of light against the vast, empty blackness of the sky: stars, galaxies, nebulae, and more. However, there was a time in the distant past, just before the Big Bang, when none of these entities had formed yet. At that moment, the universe was still filled with light. But where did this inaugural light in the universe originate? In 1965, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, were trying to calibrate a new antenna for satellite communications. They noticed a constant noise in the sky, unrelated to the sun, stars, or the Milky Way. It was present day and night and appeared the same in all directions. After some confusion, they learned that a team in Princeton had predicted this radiation. It wasn't from Earth, the solar system, or our galaxy, but traced back to the early universe's hot, dense state, the Big Bang. Over the decades, precise measurements showed the radiation was not just above absolute zero but had a temperature of 2.7 Kelvin, then 2.73 Kelvin, and finally 2.72 Kelvin. The remarkable discovery confirmed the radiation's perfect black body spectrum, supporting the Big Bang theory and dismissing alternative ideas like reflected starlight or tired light scenarios. In more recent times, we've measured that the temperature of this radiation increases as we look farther back in time, determined by its absorption and interaction with clouds of gas along the way. As the universe expands, it cools down. So when we observe the past by looking at greater distances and higher redshifts, we're essentially seeing a smaller, denser, and hotter version of the universe. So, where did this first light in the universe come from? It didn't originate from stars, as it predates their formation. It also wasn't emitted by atoms because it precedes the creation of neutral atoms in the universe. If we trace back to higher and higher energies, something intriguing emerges. According to Einstein's equation, these light quanta could interact with each other, leading to the spontaneous creation of particle-antiparticle pairs of matter and antimatter. Much like the collisions of protons at the Large Hadron Collider, which can generate numerous new particles and antiparticles due to their high energy, early in the universe, two photons had the potential to create a wide range of particles. Extrapolating from present observations, it's estimated that shortly after the Big Bang, there were about 10 to the power of 89 particle-antiparticle pairs in the observable universe. For those curious about the dominance of matter over antimatter today, a process must have favored the creation of slightly more particles than antiparticles, with the ratio of about 1 in a billion. This resulted in our observable universe having approximately 10 to the power of 80 matter particles and 10 to the power of 89 leftover photons. However, this doesn't explain the origin of all the initial matter, antimatter, and radiation in the universe. Addressing the conundrum of significant entropy, simply attributing it to the universe's starting conditions is unsatisfying. Yet, by examining solutions to unrelated problems like the horizon and flatness problems, a compelling answer to this mystery emerges. Something needed to happen to set up the initial conditions for the Big Bang, and that thing is cosmic inflation, a period where the energy in the universe wasn't dominated by matter or antimatter or radiation but rather by energy inherent to space itself or an early super-intense form of dark energy. Inflation played a crucial role in shaping the universe, stretching it flat and creating uniform conditions everywhere. It also drove away any existing particles or antiparticles and set the stage for the fluctuations that lead to overdensities and underdensities in our universe today. However, the key to understanding the origin of all the particles, antiparticles, and radiation lies in a simple fact: inflation had to end to give rise to the universe we observe today. In terms of energy, inflation occurs as the universe slowly descends down a potential. When it finally reaches the valley below, inflation concludes, converting the stored energy from the elevated state into matter, antimatter, and radiation. This marks the transition to what we recognize as the hot Big Bang. As the universe expands and cools, it undergoes a remarkable journey, forming nuclei, neutral atoms, stars, galaxies, clusters, heavy elements, planets, organic molecules, and even life. Throughout this cosmic evolution, photons, remnants from the Big Bang and echoes of the concluding inflation, persistently traverse the universe. Though continuously cooling, these photons endure, never vanishing. Even when the last star eventually fades away, those photons, having long shifted into the radio spectrum and diluted to less than 1 per cubic kilometer, will still be present. Their abundance will remain as significant as it was trillions and quadrillions of years earlier. This narrative elucidates the origin and enduring nature of the first light in the universe, illustrating its evolution to its present state. Because the universe has been expanding over the 13.8 billion years from then until now, those earliest photons were stretched out or red-shifted from ultraviolet and visible light into the microwave end of the spectrum. If you could see the universe with microwave eyes, you'd see that first blast of radiation in all directions, the universe celebrating its existence. After that first blast of light, everything was dark. There were no stars or galaxies, just enormous amounts of these primordial elements. At the beginning of these dark ages, the temperature of the entire universe was about 4000 Kelvin. Compare that with the 2.7 Kelvin we see today. By the end of the Dark Ages, 150 million years later, the temperature was a more reasonable 60 Kelvin. Over the subsequent 850 million years, these elemental building blocks coalesced into colossal stars composed mainly of hydrogen and helium. Lacking heavier elements, these stars had the freedom to form with masses dozens or even hundreds of times that of our Sun. These celestial giants, known as population-free stars or the first stars, emerged approximately 560 million years after the Big Bang. Regrettably, our telescopes are not yet powerful enough to directly observe them. Astronomers estimate their existence indirectly. Eventually, these initial stars met their explosive end as supernovae, paving the way for the formation of even more massive stars that also detonated. The era of these stellar detonations, resembling a cosmic fireworks display, was so prolific and violent that it illuminated the entire universe during a period known as Rayonization. At that time, most of the universe transformed into hot plasma. In many ways, light is the simplest particle in the universe. Even though it always moves at the speed of light, it doesn't always move through completely empty space. As long as there's matter in the universe that's transparent to light, you won't be able to avoid slowing it down. But as soon as that light heads back into empty space again, it's back to the speed of light in a vacuum, with every photon moving as if it had never moved at any other speed at all. In our universe, certain fundamental rules govern all interactions. Energy, momentum, and angular momentum are always conserved when two particles interact. The physics of a system of particles moving forward in time remains the same when reflected in a mirror, with particles replaced by antiparticles and time reversed. Moreover, every object in the universe is bound by an ultimate cosmic speed limit. Nothing can surpass the speed of light, and any object with mass cannot attain or exceed this limit. So, the next time you gaze up at the night sky or contemplate the universe, remember, the light you see has traveled a long, incredible journey from the universe's very beginning, tracing back to its origins and echoing across the cosmos.